So without further ado, with a huge round of applause, Professor Walter Röhing.
Thank you, thank you, thank you. Friday, I need musical instruments. There's one instrument missing. I prefer a trumpet, but it doesn't have to be a trumpet. But it has to be a wind instrument roughly this size. Not this size, but this size. I read a bassoon, which is this size, that's fine. This size. Trumpet would be great. Oboe would be great. French horn would be great. The more special, the better. Send me email to this address, and by all means, come up with an instrument that fills that gap that I have, this side wind instrument. I will erase this for obvious reasons. How many of you, or who, I should say, has ever seen rainbows? At least that's what you think. I bet you've never seen one. You've looked at some, oh yes, just like you've looked at art. But you've never seen art unless you're educated. After today, your life will change, because I will make you see for the first time in your life the rainbows. Unless you have already watched my lectures on rainbows, of course, which is possible. Answer these 6 questions. We can see how well you know rainbows. The first question is, what is the radius of a rainbow? And what I mean by that is the following. A rainbow is a circle, right? Something like this. So somewhere, perhaps below the horizon, is the center of that circle. And so the question now is, what is this radius in degrees? Or is it not always the same? Then comes the issue of the color sequence. If you see a rainbow, is the red always on the inside or always on the outside, or does that depend on the time of the day of the week? Have you ever noticed that there is an enormous difference in the brightness of the sky between here and there? And if so, where is it bright and where is it dark? Have you ever noticed a second bow? And if you have noticed it, where do you look for the second bow? And then comes the question, what is the color sequence of the second bow? Is that the same as the primary bow, is the bright one, or is it reversed? Who can answer all those 6 questions, by the way? You've seen my lectures, right? Only one person. That's an insult. Only one person has seen my lectures. Who can answer 5 questions? You can't answer 6. 5, you can.
Yes.
4, 3, 2. Who can only answer 1 question? I won't embarrass the rest of you. 0, right? Before I talk about the rainbow, I have to introduce you to what we call in physics refraction. when light goes from one medium to another medium, and I choose here for obvious reasons air to water, so if light comes from air, I take a narrow beam of light. Think of this as a very small beam of sunlight, very narrow. It comes in here. Then there are two things that always happen. One is that some of that light is reflected. Goes back. And this angle alpha is the same as this angle alpha. We call that reflection with the L of Lewin. Part of that light goes into water, and this angle we call beta, and that is not reflection, but that is refraction with an R. Each one of these media have what let's call this medium 1 and this medium 2. They have an index of refraction with the R. We call this N1, and I call this N2. And the index of refraction tells you what the speed of light in that medium is. Air and vacuum, very close to 1.00. That means that the speed of light in air is about the same as in vacuum, which is 300,000 kilometers per second. That's what 1.00 means. But in water, it is approximately 1.33. I will be way more precise later, because that's important for the rainbow. That means that in water, the speed of light is 33% lower than it is in air. That is the meaning of the index of refraction. A Dutch scientist, his name is Willibrordus Snelsius, in the 17th century discovered the connection between alpha, beta, and ends. And that connection is as follows. N1 times the sine of alpha equals N2 times the sine of beta. Now I realize there are people in the audience who say, well, now I might as well leave because I don't know what sine is. Well, I'm going to tell you what the sine is of an angle. If this is alpha, and I draw here a line, and this is important, that must be perpendicular here. We indicate that normally with this sign. That means this angle is 90 degrees. If the length of this side is A, and the length of this side is B, then the definition of sine alpha is simply A divided by B. Nothing more, nothing less. So, I can write several angles for alpha and the sine of alpha. If alpha is 0 degrees, then the sine of alpha is 0. That should be immediately obvious, because if alpha is 0 degrees, then A is 0, so obviously the sine is 0. If alpha is 30 degrees, it's a little less obvious, the sine of alpha is 0.5. If you have a little calculator which has signs on it, you can confirm that. And if alpha is 90 degrees, then the sine of alpha is 1.0. That's the best I can do for you today. I will give you one example whereby I apply Snell's law. I take air, which has an index of refraction 1, and I take water, which I take 1.33 for now. And I make the angle alpha, I do that purposely, I make the angle alpha 60 degrees. I can do that. I can choose that angle at which it comes in. I apply this equation. This is 1. This is 1.33. Here is the sine of alpha is 60 degrees. So I can calculate what the sine of beta is using Snell's law. And if I know what the sine of beta is, then I can calculate what beta is. And beta is then 40.6 degrees. So this is an application how Snell's law works. Very simple, very straightforward. And this specific example, I'm now going to show you with a demonstration, which is set up in almost exactly this way. It's set up here. If we can turn the lights off, because it's important that it's dark. You see light coming in from the right side. The fact that it's green is just because we have a green laser. Alpha is roughly 60 degrees here, at least I chose it that way. We call that angle, by the way, the angle of incidence. The angle between the incoming light and the vertical on the surface is always called the angle of incidence. So the angle of incidence is about 60 degrees. You see some of that light being reflected, and you see some of it going in, and that must be then very close to an angle beta of about, what was it, 40 degrees. So far, so good. Can I have the lights back on again? Okay. Now hold on to your seats. This is one drop of water. And sunlight is coming in here from the side. Everywhere on half the surface of that raindrop. I have chosen one very narrow beam of all that sunlight. It's only a small fraction of the total. And I have an angle of incidence here, which I have chosen to be roughly 60 degrees. Remember, angle of incidence is the angle between the incoming light and the line perpendicular to the surface. That is, this line is perpendicular to the surface here. At that point A, two things happen. A little bit of light reflects, and the remaining light refracts. That is Snell's law. I call that angle, therefore, R. I call this one I for angle of incidence. So this R does not mean reflection, it means refraction. It reaches point B inside the water drop. At point B, two things happen. Some of it goes back into the air. That would mean refraction. And some of it gets reflected. And therefore, this angle is the same as that angle. Because you see, this angle here is the same as that angle. So this angle R is the same as this angle R. Now it goes on its way to C. At point C, a little bit of that is reflected, goes back into the water, and most of it comes out. That means refraction. And if you spend the time using Snell's law here, using the refraction law here, so you use Snell's law here, then the reflection here, and you use Snell's law here again, you will find out that this angle here happens to be I. It's no big deal, it may take you a few minutes to demonstrate that. Now look at this line. The light came in like this, and it comes out like this. And I call this angle, this is the change in angle. It came in like this, and now it's doing this. I call this angle phi. And for those of you who've had a little algebra, they should be able to prove that phi equals 4r minus 2I. May take a minute or two. I can help you already a little bit because there is 1, 2, 3, 4 angles of r, and there are 2 angles of I. Just comes out to be 4r minus 2I. If I take this narrow beam, then I hope you see that the angle of incidence is 0. So it goes straight through according to Snell's law. It reaches this point, it refracts back, and it comes out in this direction, and so phi is 0. That checks, because if I is 0, then r is 0, and therefore phi is 0. So that simple case works. Now there's something very, very interesting. And that is, if you change these angles of I, this I is 0, and when light hits the water drop higher up, I increases and increases and increases and increases, then phi increases but reaches a maximum value, which I will call for now phi maximum. Oh. I have chosen here an index of refraction 1.336. I will be more specific what I choose later on. I picked this one. Sine of I is n sine r. I left the n1 off because n1 is 1 anyhow. It comes from air to water, and the n that you see there is the index of refraction for water. I take a value of I use Snell's law, and I'll calculate r. So it's very simple. Anyone can do this. I go up in 10-degree steps, I use Snell's law, and I calculate these values for r. I use the equation phi equals 4r minus 2I, and I come up here with values of phi. Nothing special, except there is something that you wouldn't expect, that phi reaches a maximum value, and when you go to higher values of I, then phi goes down again. And this, as you will see very shortly, plays a key role in the formation of the rainbow. The index of refraction depends on the color of the light. What you see here are the index of refraction for red light, and here the index of refraction for blue light. You may ask, why do you stop at blue? Because the light from the sun all the way goes up to violet. Well, there is very little violet light in the sun. There is some, I must admit, but when you see rainbows in general, you hardly ever see violet. So I decided to cut off as blue, but you could extend this to violet if you really insisted. I have a way of finding out for what values of incidence I get phi maximum. It's part of my courses. It's not an easy calculation, but it's doable. You need some calculus to do that, so I will not discuss that here. But what is important, that you see that if the angle of incidence for red light is very close to 60 degrees, that phi maximum becomes 42.3 degrees. That means this angle here can be smaller than 42.3 degrees. That's allowed, but cannot be larger. That's the largest value. For blue light, the angle of incidence is slightly lower, and the phi maximum is 40.7 degrees. That means blue light can come out at any angle here, phi, smaller than 40.7, but not larger. We'll have to hold on to this because this is very important. So now comes a key question. I have one water drop here, one water drop, and I have sunlight falling onto that one water drop, coming from this direction. What is this one water drop now going to do with that white light from the sun that covers the half of the raindrop? I'll first give you the answer, and I'll do it first for red light. I separate for this moment out only the red light, but of course I'm going to do it also for blue light. A cone of light will come out of this drop, and that cone will be filled with red light. But the angle cannot be larger than 42 degrees, can be smaller than 42 degrees, but not larger than 42 degrees. Because this angle phi here cannot be larger than 42 degrees. You see this? It was specially made for me years ago, 42 degrees. I take 42 to round off phi maximum. In other words, this is possible. And this is possible. And any angle smaller than that is possible. So it is a cone of red light. To make you see that it is a cone, I will do this. That may help you. Why is it a cone? Because after all, I have here only one line, one beam, and only one beam comes out. This is a water drop. This line goes straight through the center of the drop, which is this line. And this line here is light that comes in, that is this one. It refracts, reaches this point, reflects, goes to point C, and it comes out. And if this angle of incidence is 60 degrees, this has to be red light. You see it is. So this angle here is then 42 degrees. But the entire surface of this water drop here is illuminated by the sun. And so this is not the only direction for which the angle of incidence is 60 degrees. There's an enormous number of them for which the angle of incidence is 60 degrees. Do you see on this water drop the black line? Any beam that comes in anywhere on that black line has an angle of incidence of 60 degrees. So it's going to do exactly the same as this one is doing. And I will make a small change which makes you see that. Suppose I this is the raindrop. Suppose I let the light now come in here. It's on the black line. So the angle of incidence is 60 degrees. It's refracted, it reflects in the back, and it comes now out here. If this angle of incidence is 60 degrees, then this comes out at an angle of 42 degrees, and this is red light. So I've shown it to you for two locations, but if you do it for every single rotation and every single location, you obviously get a cone. So this is then just one side of the cone, and this would be this side of the cone. So you get a cone. Now I'm going to do the same for blue light. I can be a little quicker. I think we should agree that this angle is now very close to 42 degrees. I just round it off. I don't take 42.3. So now I have another cone which is completely filled with blue light. but can no longer be outside, cannot be outside this angle, which is slightly smaller. That's the 40.7 degrees. And that's also a cone of light. And all the other colors that are in the sunlight, I have not drawn here, they're going to be in between. They have clearly phi maxima, which are between the 40.7 and the 42.3. So I only have taken the two extremes. So the light comes in, and I restrict myself. And I underline that because I'm going to change that later. I restrict myself to light that refracts first, then reflects, and then refracts. That's all. I restrict myself to that journey. Refraction, reflection, refraction. So, how about the light here? Isn't there any light? When the sun shines in, that this water drop brings light there. What is the answer? Is that angle larger than 42 degrees? Yes, so it's impossible. So there is no light outside this cone. No light. What would be the color of the light inside here? Remember, the red light is everywhere in this cone, as long as it's smaller than 42 degrees. So the red light is also there. I haven't drawn it because it would be very confusing. The blue light is everywhere in this cone because it's allowed to be smaller than 40 degrees. That means all the colors that I have left off are all coming out here. So what do you think the color is that I will see if I looked at that? White light. So here, this inner portion is white. If I project this on the wall, and that's an experiment that I'm going to do later, then I would see the following. So I have one water drop, a bright light onto this water drop, and I'll show you what you see on the wall, and you will see the following. Red, blue, and I'll be even so kind, you might as well see green too, and all the colors are inside here. And when you see that on the wall, which is an experiment that I will do later, there will be no light here, because it's outside the cone, and inside here is white light. And here, you see all the colors of the rainbow. Now, if there is a smart physicist in my audience, and I'm sure there's more than one, he will say, Walter, you're cheating. Because if right here, where the blue comes out, if all the other colors can also come out, which they can, because this angle is smaller than 40 degrees, so red can come out, green can come out, all the colors can come out, including blue, then the inside should be white. And that's a very good question, and I'll give you the answer why it's not. I'm going to make you now a curve, a plot of the light intensity as a function of phi. And this is the intensity of the light. And I'll start with red. So for low values of phi, this is the light that comes out. And when it reaches the maximum value, it peaks. And this then is 42 degrees. It cannot go beyond 42 degrees. The green light goes like this, and when it reaches its maximum value, it peaks. Cannot go up to 42 degrees. The blue light goes like this, and then when it reaches its maximum value of phi, it peaks. But it cannot go any further. And so it is true that here all the colors are present at equal intensity, so you see white light. That is here. That is here. But because of that wonderful phenomenon that the red spikes up and the green spikes up and the blue spikes up, right at the location of the blue still dominates. And so you don't even notice the other colors. You really see very distinctly bright blue light when you will see a rainbow. Now we have to start looking at the sky. I'm standing here. And the light from the sun comes in like this. The sun is infinitely far away, so all these lines are parallel to each other. Light comes in like this. I look in this direction. I can pick a raindrop here, 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 or pick a raindrop there. They all do the same thing. They all cast this cone in the direction of the sun with that angle. So I will draw one. I only do the red because otherwise it will take me too much time. So here is one cone. I could leave this off, but this may help you. When you look in this direction, would you see light? You would see no light because you're outside the 42-degree angle. So the same reason why you won't see any light coming from there is that there is no light here. Now we're going to look in another direction. We're going to look here. Doesn't matter whether I take a raindrop here, or here, or here, or here. Let's just pick this one. They would all do the same thing. They produce the 42-degree cone in red, 42 degrees in red. What color do you see? Oh, come on. If you can't answer that, I have failed as a teacher very badly. White! Yes, you're looking straight in the heart now of this. You're looking right in here. Look at this. You're looking straight in the middle. It's white light. Now, we're going to choose another angle. I'm going to choose an angle in this direction. It doesn't matter whether I take a raindrop here or whether I take a raindrop here or a raindrop here or here or here or here. Makes no difference. I go here and it will cast into the sky a famous '42-degree angle 42-degree angle, because that's the angle that I have chosen here. If now I look in this direction of the sky, what will I see? And only red, no other color. And so now you understand, if you look here, no light. If you look here, white light. If you look in this direction, then you see the red light. And of course, you have to look a little lower in the sky to see the blue light, because the angle is smaller than 42 degrees. Now, let's suppose the sun is there, and I'm standing here. By the way, if this is you, then this is your shadow. You realize that? Guys, this is your sun, right? So this is the shadow on the ground. So there's the sun, and there's my shadow. And as long as I look 42 degrees away from this line, red. But because it is a spherical object, it doesn't matter whether I go 42 degrees this way, or whether I go 42 degrees that way, or 42 degrees that way, or 42 degrees that way. And that explains why the rainbow is a bow in the sky. As long as it is 42 degrees away from this line, in any direction, I see red light. And a little lower in the sky, I will see the other colors. I will see the blue light. When this lecture was over, I looked at the blackboard, and I noticed that I drew this line incorrectly. Clearly, this line here has to be parallel to this line, which it is, but it should also be parallel to this one, and it is not. So allow me to correct that. I'm taking it out. And now I'm going to put in the right direction. I go right here, go to this point here. And now it is in the right direction, and I want to emphasize that this person is still seeing white light, so none of my conclusions were wrong. Sorry. And so now I can make you a picture of a rainbow. So here we have, say, the horizon. Oh. I see a rainbow here. The center could be somewhere here, below the horizon. This angle, which we call the radius of the rainbow, is 42 degrees. The blue light, closer to 40 degrees, is here. So with this bow, the red is always on the outside, and the blue is always on the inside. And this, by the way, but I don't want to confuse you, is the angle that the sun is above the horizon. But that's a detail now. That's what you will see. Now I'm going to include two reflections in the raindrop. Not one, but two. So now we get refraction, reflection, again reflection, and then refraction. So inside the water drop, the light reflects now twice. And I go through all this hocus pocus again, and I come to the conclusion that now there is not a maximum value for the various colors, but there is a minimum value. It cannot be lower than a certain value, but it can be higher. And when you calculate then something very similar, you will find that the second bow is formed in the sky. It is 10 degrees above the first one, and the colors of that bow are reversed. In other words, red is on the inside, and blue is on the outside. The bow is much fainter. It has two reflections inside, and this angle is roughly 52 degrees. The secondary bow, we call this, is almost always there. But most of you may have missed it because it's much fainter than the primary bow. For one reflection, the light can never appear here. Here, there is no phi maximum, but there is a phi minimum. So the light can never be here. So this bow says no light here. This bow says no light here. So this is dark like hell. And this has a name. This is called Alexander's dark band. Since this bow is formed by phi minimum, that means light can come out at an angle phi larger. There is again some light here, some light. And now I want to show you some slides which will make you see what we have just discussed. So let's make sure that we have everything on the board that is relevant, that we have that up. And so if we can have darkness, and I need my laser pointer. And can I have the first slide, John? What you see here is nothing new. This is basically what I have drawn. The sunlight comes in here. This is Walter Lewin. This is his shadow here on the floor, on the ground. And if I look at a water drop, which is 42 degrees away from this, what I call reference line, this drop will be red. If I look in this direction, I see no light. If I look at 40 degrees, I would see blue. If I look at a lower level, it would be white. Even if the water drop was near my feet, as long as this angle is 42 degrees, this drop would look red. Next slide, John. This is from famous physicist Newton, who was one of the first to understand the rainbow. This is from his book, Optics. And you see here the primary bow. If you're sitting in the front row, you can see a similar situation that I drew. Here is refraction, here is reflection, here is refraction. This is the secondary bow. If you look very carefully, if you can see inside the drop, you would see two reflections. Next slide, please. This is fun. You should do this. You probably have already done this. When you spray your garden, sun is high in the sky, your shadow is here, your head, 42 degrees away from this line, red. And when you see here, it's red, and it's there, it's red. Everywhere 42 degrees, it's red. And if you turn around and look back, it is red. So you can make a rainbow encircling you. Circular rainbow all the way around you. Next slide. Oh, boy. Sunshine Rainbow Maker. And you can buy all that for $12. But it is a fake. Why is it a fake? Why is it absolutely a fake? What?
Colors are reversed.
Yeah, red is not on the outside. So this is a spectrum of something, but it's not a rainbow. But it is very typical if you want to sell something called misleading advertisement. Next slide, please. This is a beautiful painting from the 6th century in Western Asia. There is a hand here, so that makes reference clearly to the Bible. I do set my bow in the clouds. What is interesting here is that the artist chose only two colors, blue and red. I don't think that's because he missed the other colors in the rainbow. I think it's a conscious decision that he may have made as an artist. There is, of course, another possibility that the physics in the 8th century was different. So maybe in the 8th century, red was inside and blue was outside. I would rather argue that this was a conscious decision that he made just two colors and he reversed the order of the colors. Next slide, please. Okay, in 1972 was the first time that I lectured in 26100, and I lectured 803, which is the course for the vibrations and waves. At that time, we had 500 students in 803. I decided that I was going to cover rainbows during that lecture. There was no internet. I had no pictures on rainbows, so I decided I have to make them myself. So I asked my daughter, who was 7 years old. By the way, it was January and it was freezing. It was terrible. I asked Emma to go out with me in the garden and spray water around from a hose, and I would then take the pictures of the rainbow. And you see that here. You see beautifully the red on the outside, you see the blue on the inside, you see this white light. You understand now where that white light comes from. I explained that. You see that no light from these raindrops come to me. That's why you can see the forest so beautifully. The reason why you don't see the secondary is probably that the light was not strong enough, or more likely that the water was not present there. If there's no water, of course, you cannot have a rainbow. So the water may not have sprayed up high enough. Now you're going to see a picture that breaks my heart, but it has broken my heart so many times. This is Emma. And Emma was crying. It was so cold. That was the first time that I told her, Emma, sometimes you have to sacrifice for the sake of science. Since then, she's done it countless times. And right now, she loves it, because this picture is at least in 4 books. So now she's very proud of this picture. Next slide, please. I also tried to make a secondary bow. And therefore, I chose my driveway, which is very dark. So you need a very dark background to see very little light. And so here, Emma was again on the left side, spraying water. You clearly see the primary. You see white light coming in from here. And here you do see the secondary. And if you look carefully, you can see that the colors are reversed. You see that red is on the inside and blue is on the outside. Next slide. I got this picture from Michael Sorgi. He took this, I think, somewhere in Belgium. There was a waterfall. You see the water of the waterfall. You see white inside the bow, very white light, red on the outside, blue on the inside. No light is coming to you here, and therefore you can see beautifully the forest and you can see the city. Why don't we see the secondary? Probably because there is no water here, because the water of the waterfall didn't spray high enough. The next slide. Now you see it all. These are the famous VLA radio telescopes in Socorro, New Mexico. The primary bow, red on the outside, blue on the inside. Alexander's dark band, you can't miss it. Really dark. The secondary bow, red on the inside, blue on the outside. And here you see again sunlight. Remember I told you why outside the secondary you see again sunlight. If you look closely, you see that there is something strange with the blue. It looks like there are dark bands running through the blue. We call those bows supernumerary bows. And they are caused by very small water drops, 1 millimeter or smaller. Everything I've told you so far is what we call geometric optics. But if the water drops become very small, then you cannot ignore the fact that light is also a wave. And the interaction of the wave with the very small drops causes what we call in physics diffraction. And when you have diffraction, red color can destructively interfere with red and make darkness. Red can constructively interfere with red and make bright. And that is very typical for diffraction, that you see in addition to bright colors, you begin to see dark bands. And you see them very well here inside this bow. So you can almost be certain that the rain there, the raindrops were 1 millimeter or maybe even smaller. If the water drops are very, very small, and I'm talking now about something like 30 microns or so, then the diffraction becomes so important that all the colors are smeared out over each other. The red is over the blue is over the green, it's all smeared out. What color will you now see? White. That's called a white rainbow. They're rare. They're also called fog bows because fog has small water drops which are also typically of size 30 microns. And so you can often see white fog bows, which is exactly the same as a white rainbow. I gave lectures on rainbows. 1972 was the first time. And there was a student, Carl Wales, at that time in my audience. And the next year, during the summer, he went to the North Pole. And he was 340 miles from the North Pole on Fletcher Ice Island. It was 2 o'clock at night in July. The sun is above the horizon then. And he took pictures of white rainbows, and he sent me those pictures, and I want to show you the first one right now. There you see a white rainbow. And if you look very closely, you may see a dark band here. That is undoubtedly the result, again, of diffraction. But keep in mind, the fact that the bow is white is already the result of diffraction, namely that the water drops were so small. So it's very common when you see a white rainbow that you also see dark bands. The next slide will show you a close-up. Let your eyes get used to it. You see here a white rainbow, dark band, white rainbow, dark band. Very typical for diffraction. Now, I'm asking you a question. Suppose there is a rainbow at sunset. What would you expect to see? Or sunrise, for that matter. What would you expect to see?
Red color.
Red light, because there's only red light. What happens with all that white light inside the bow? Would that not be there? It would be red too. Very good. So if you only have red light to work with, you get a red rainbow, and the white light has to be red because that's all there is. And so if you look at the next slide, you see a red rainbow. Isn't that remarkable? How all that white light inside the bow is now red. Okay, can I have lights again? You see here the 6 questions. If I was going to answer these questions with you, that would be an insult to you. Clearly, you should be able to answer these questions now without any difficulty. And if you can't, then you can still watch my lectures on the web, on rainbows, and then it will sink in. Each one of these questions should now be duck soup, and this may be the first time that you are able to answer them. So now comes the time that I'm going to make you see not really a rainbow, because if I wanted to do that, we would rain everywhere here in the audience. That wouldn't work so well, and I probably would be in trouble. But what I can do, I can use one water drop. It's right here. I can shine white light onto that one water drop. That one water drop will then produce this cone, red on the outside, blue on the inside, white light here, no light there, and I can show that on the screen. So you will see everything that is important in understanding the rainbow. But the actual rainbow itself you won't see, because for that you need a situation that you hear, that you look at millions of raindrops and look at all these individual cones. So I will only show you this projected on the wall, so you will see this. So Bill, may I ask you carefully to move this right in the middle of the lecture hall. Do it quietly, there is no rush. I don't want you to get into trouble, and it is a very delicate instrument. Can easily go out of alignment. All right, I think I have it there, Bill. You see here the one drop. Bill, can you lower the screens, please? The light comes from here, from behind, shines right into the audience. You don't need sunglasses because I'm going to put a shield here so that you will not be blinded by the light. The light hits this drop, and out of this drop comes that cone. And that cone we will project on the screen. So I'll put this here to protect your eyes. Don't put your expectations too high. After all, it's only one drop. And there is a saying in this country, you get what you paid for. The light is faint. I therefore want your eyes to get used to the darkness, for which I give you about 30 seconds before I turn on the sun, and you will see, hopefully, I call it rainbow, but it is the result of that cone. All right, Bill, if you make it dark now. And there it is. Unmistakable. Red on the outside, blue on the inside, white light here, no light there. Exactly what I told you. And you now understand why that is. There's no hope on a secondary because we don't have enough light for that. But you see here all the features that you can expect from a rainbow. Next time you see a rainbow, you will look at it very differently. You will check that the red is on the outside of the primary bow, and you will search for the secondary bow, which is about 10 degrees higher in the sky. You will also make sure that the color sequence of the secondary is reversed. And you will make sure that the inside of the bow, that the sky is much brighter than on the outside of the primary bow. And for sure you will try to see Alexander's dark band. This is like a disease. You can't resist it. And it's all my fault. I cannot cure you anymore. It's too late for that. This is a disease for life. But all this joy and fun that you will get over and above the everlasting beauty of the bows, but you will see much more than people who do not have the knowledge that you have now. And therefore the experience for them will be rather shallow. Knowledge always adds. Knowledge never subtracts. Knowledge is hidden beauty. Your life will never be the same. See you on Friday.